Math 2414, review, trig identities, double angle identities. In the previous video, we created, or in some cases just wrote down, some identities involving sums and differences of cosine, sine, and tangent. And if you're wondering why I didn't do any for secant, cosecant, and cotangent, because a lot of times we don't do trig in those things. Could we derive them? Absolutely. Do I challenge you to try them? Absolutely. Have fun with that. It's not impossible, but it's a good academic challenge. You'll notice I've only written the sum formulas, cosine alpha plus beta, sine alpha plus beta, tangent alpha plus beta, because I'm going to use those as a springboard to get what are called double angle identities. Now, these three, a lot of people don't remember, but the next ones, you should. Let's start with cosine of 2x. By the way, a double angle is exactly what it sounds like, an angle that looks doubled because it has a 2 in front of it. Now, how do we create a double angle identity? Well, the trick to creating a double angle identity is to remembering that something like 2x is just x plus itself. So let's write this as cosine of x plus x. Now, why is that advantageous? Because I have a formula for cosine of the sum of two angles, alpha plus beta. I stick the angles here. However, in this case, my angles are the same, and I'm replacing them both with an x. In other words, if I put an x here and an x here, I would get cosine of 2x. So let's replace an x everywhere I see an alpha and x everywhere I see a beta. So cosine of alpha, so cosine of x, cosine of beta, another cosine of x, minus sine of alpha, so sine of x, sine of beta, so sine of x. Again, all I'm doing is taking this formula and letting both alpha and beta equal x simultaneously to give me this, which is equal to that. And we get this, but I can write it a little bit cleaner because cosine x times cosine x literally means cosine squared x minus sine x times sine x is the definition of sine squared x. So that's not bad. That tells me how to find the cosine of double of an angle if I know the cosine and the sine of the individual angle. So here is a variation of cosine of 2x. However, there are two other variations. Does this look familiar? Well, sort of, but not really. It kind of looks like a Pythagorean identity. Anytime you're doing trig, whether it's in calculus or not, and you see squared trig functions, you should start saying, is there something I can do with this to maybe make it look better or different? And the answer in this case is yes. This is not equal to 1. If it were a plus, it would equal 1. And no amount of shuffling this around is going to make it say cosine squared minus sine squared. The reason's pretty simple. Currently, they have the same signs, S-I-G-N. They're both positive. Here they have opposite signs. The only way I can make them have opposite signs is if I move one to the other side of the equal sign, and therefore I can't create cosine squared minus sine squared here. But I can take advantage of this Pythagorean identity if I take advantage of a variation of it. For example, if I isolated the sine squared, it would say sine squared equals 1 minus cosine squared. So what would happen here? In fact, I'm going to do a divergence here. What would happen here if I took out the sine squared after the minus and replaced it with what it equals, which was 1 minus cosine squared? So let's just say that we replace sine squared x with 1 minus cosine squared x. If we did that, it would look like this. And cosine squareds don't cancel. They look like they cancel. One's positive and one's negative. But this one is inside of a parentheses with a minus in front. The minus would get distributed, which should actually make this positive. So we would have cosine squared plus cosine squared, which gives me 2 cosine squared x. And then we would have a minus 1. This is another variation of cosine of 2x. I'm going to summarize them all in a moment. But that was based on the choice of replacing the sine squared with something it equals. But what if we replace the cosine squared with something it equals? Well, if I take this Pythagorean identity and solve it for cosine squared, it says cosine squared equals 1 minus sine squared. So I could take out the cosine squared and replace it with 1 minus sine squared. And then minus the sine squared here. In this case, the parentheses aren't necessary. There's nothing in front keeping them there. So we can just drop them, have a 1, and a pair of minus sine squared x's, so minus 2 sine squared x. And this is variation 3 of cosine of 2x. This one's actually a good one to write down. Cosine of, we'll just say 2x, is equal to 3 different identities. Cosine squared x minus sine squared x, 2 cosine squared x minus 1, and 1 minus 2 sine squared x. And if you're wondering, do I need to know all 3? No and yes. No, because some of these occur more often than others, but these bottom 2, I would know them, and you'll see why soon. Alright, so we've got 3 variations of cosine of 2x. It's either cosine squared x minus sine squared x, 2 cosine squared x minus 1, or 1 minus 2 sine squared x. For sine of 2x, I'm just going to set it over here, because it's actually pretty easy to see. For sine of 2x, we would play the same game, but we would play it on this identity by replacing both the alpha and beta with x's. If we did that, we would get sine x cosine x plus cosine x sine x. We can't write as squares because we're not multiplying the same trig functions like we were up here. But, and you know what, I am going to write it down. Sine of 2x is the same as sine of x plus x, but using the sine addition formula, sine of alpha plus beta equals, and replacing all the alphas and betas with x's, we would get sine of x cosine of x plus cosine of x sine of x. Again, we don't have any squares because we're not multiplying like trig functions. However, if you notice, the 2 halves of the addition problem are like terms. This is sine x times cosine x, and so is this. Yeah, I know it's written the other way around, but multiplication is commutative, so it's not a big deal. I've got one of these, I got one more of them, so altogether I've got 2 of them. And we could write it a couple of different ways, but we'll just say 2 sine x cosine x. This identity only comes in one variation, one convenient variation, because unlike the cosine one, we didn't have any squared trig functions that allowed us to play games with that first Pythagorean identity. But this is one that you really should just know. Sine of 2x equals 2 sine x cosine x. And if we did the same thing with tangent, well, we can just talk this one out. If we did the same thing for tangent, by taking the tangent sum formula and replacing each alpha and beta with an x, we would have tangent x plus tangent x. So we would get 2 tangent x. And then 1 minus, on the bottom we would get 1 minus tangent x times tangent x, but that would be 1 minus tangent squared x. At which point you might be thinking, ooh, you want me to grab a Pythagorean identity and do something down here. Well, if something nice would happen, but it doesn't. The second Pythagorean identity says what to do with 1 plus tangent squared. It doesn't say what to do with 1 minus tangent squared. Could we solve this for tangent squared? Make it say tangent squared equals secant squared minus 1 and put it here? Yes, but it really wouldn't make it any better. The ones would not cancel, despite how you might think they would. Play it out and you'll see what I mean. And then we would get an identity that contains tangents and secants instead of just tangents. So I think this is the best variation of tangent of 2x. All right. Yeah, as far as these go, I would really know these 2. The tangent one shows up on rare occasions, and if it does, you might just want to go back and review it. But I would definitely know cosine of 2x and sine of 2x, especially the 3 variations of cosine of 2x.